How do you know when you have to integrate to get the electric flux? Definition of electric flux is in terms of an integral. Phi E is the integral of the electric field vector dotted with the area vector. Now, in general, any vector can be written in terms of components. So let's write the electric field as Ex I hat plus Ey j hat plus Ez k hat. And similarly, we can write the area element vector as an x component, a y component, and a z component. Now, when we dot those two vectors, we get a scalar integral, and it would simply be the sum of the x components, the y components, and the z components. Now, how do you know which integral to use, whether you need to use more than one? Well, that all depends on the area that you're trying to get the electric flux through. So in general, if we draw a box that sits on the x, y, z axes, and we'll have this box be A wide, B deep, C high. We'll let that be the x axis, y axis, and z axis. So each of these faces of this cube has an area vector, and if it points in the y direction, it would be AY. If it points in the x direction, it would be AX, and if it points in the z direction, it's AZ. So those faces each have a unique direction for their area vectors. So let's just take one face. Let's say we just take the front face of this cube. So we're only looking at the z component of area, which means the only integral that would come into this calculation would be this one. There is no ax and there is no ay, so those two integrals would be 0. All right, so we're down to an electric flux integral that has a z component of electric field, the az, and an area vector that points in the z direction. Now, the question is this an integral or is it not an integral? So we have to look at Ez to decide whether it's an integral or not. So what are the possibilities? Case 1. Ez is constant everywhere on that face. So, for example, if Ez were just a number like 6, then the electric flux would simply be the integral of 6 times dAz. The 6 comes out. The integral of dAz is just the sum of all the little elements of area. So it's just 6 times Az. And for our face, that would be, the area of Az would be A times C. So it's be 6AC. And that's the answer. No integral necessary. Okay. Case 2. Ez is a function of z only, which means that Ez only has constants and z's in it. So let's say that Ez is equal to 3z squared. Well, we'll see in fact that on that face, z has only one value. On this face, z is always equal to b. So, in fact, even if z appears in the formula for Ez, it is really a constant, because Ez would be 3b squared, which is a constant. So once again, we don't actually have to integrate. We put in 3b squared times az, daz, and we get again 3b squared times the area of az, which is a times c. So once again, we didn't have to integrate. So let's try case 3. Now, Ez is a function of x. So for example, Ez would be 3x squared. Now, if you look at this face, x changes over this face. X changes from 0 to a. which means that the electric field over this face is getting bigger as I move to the right in the x direction. So maybe on this side it's just small, then it gets bigger and bigger and bigger. So this case we definitely have to integrate. And we have to divide the face into vertical strips, where on each strip z is actually constant. And so the width of our strips will be dx, and our integral will now become the integral of ez daz. So it's the integral of 3x squared. Now the area of a strip is the width dx times the height. And in this case our height is c. So go back, put times c. And x runs from 0 to, oh, better be careful where x runs. X runs from 0 to a, over to this edge where x equals a. So our integral goes from 0 to a. Alrighty, so we do this integral and we pull the 3c out. We get x cubed over 3, evaluate from 0 to a, and we ended up getting ca cubed. And that's the answer to that integral. Now you can probably figure out if it's a function of y, ez is a function of y, then it means that the electric field, let's draw this again here, the electric field on this face, this is x and y, is now increasing as we go up. So it's coming out and it's getting bigger and bigger as I move up, which means I want to divide this into horizontal strips, where in each strip the electric field is constant. So now I use my dy for the width of the strip and a for the length of the strip there. So now my integral becomes ez. Oh, let's pick something. So let's say it's oops, something on the screen there. I'll just pick something, 3y squared, and then daz would be dy times the width a. And y now runs from 0, oh dear, something on the screen, 0 to b. Alrighty, so once again, the 3a comes, now I better check that that's what y runs from. So y is 0 to b? No, y is 0 to c. Okay, so that's not right. Y is 0 to c. 0 to c of y squared dy. So it becomes 3a y cubed over 3 from 0 to c. That's wrong. And that's ac cubed. Alrighty, and that is how you decide if you're going to integrate to get electric flux.